Last but not the least, it's a pleasure to have Florent Krzakala to give a last presentation of today. Florent doesn't need introduction to this crowd, of course. Gave a very nice bootcamp talk late August. And the only thing I will remind, and as Florent and Lenka would like to remind others, is that they are moved to EPFL and happy to host lots of visitors. And I plan to take advantage of that as soon as COVID situation permits that. So, with that said, the floor is yours.
Thank you. Thank you. I assume everyone can hear me well? All right, let's start. Yeah, thank you for organizing this. And yes, it's a pleasure to feel connected to all of you and to listen to the talk. And I hope we will, meet again in real life soon enough. All right, let's go. So I want to discuss phase retrieval today. So the problem doesn't really need introduction, but I'm going to give one anyway. So you have a vector x, which you don't know. And what you know is instead is the modulus of the projection of this vector. So you have a matrix A, you multiply it by the vector, and you take the absolute value. If this is a complex problem, or you take the modulus if it is a real one. And then you have measurement. So you are given y, a, and you try to reconstruct x. All right, what I want to discuss here is slightly more specific. And in the spirit of many problems in this workshop is what happens if you are doing random measurement, and in particular random projection. So here the matrix A is chosen randomly. So let's assume that A is a random matrix. Pick your favorite one, IID matrices with Gaussian coefficient, or maybe a random rotation matrix, subsample DFT. There are many interesting problems. Now, X instead would be, at least in the first part of the talk, just a normalized vector. Okay, so think about X sample uniformly on the sphere. And I will discuss more interesting or more challenging situations on X later on. And so these are the questions you want to know. Okay, how many observations does one need to recover X better at a random guess, at a weak recovery? Perfectly, but strong recovery, and what algorithm should you use, right? And of course, I'm going to discuss the high dimensional limit when both m, number of measurement, and d, the dimension of x, goes to infinity together with a fixed ratio. All right, so let me essentially spoil the fun and give you the answer right now. So for weak recovery, in order to beat a random guess, these are the answers. Okay, it's easier to state them with this notation where the real case is beta equal 1, complex case is beta equal 2. So if your matrix is just IID Gaussian, the answer is known for real, and in fact also for complex case, thanks to this very nice work by Marco and Andrea. And the answer is just, you need m over d to be larger than beta over 2. Okay, so 1/2 for real and 1 for complex. For random orthogonal matrices, or a random rotation matrix, if you want, well, the answer is also known, and it was due to this work in the team of Ariane Maleki, and it's actually harder. It's m over d is larger than 1 plus beta over 2, so it's actually a more difficult problem. So one of the first contributions we had was to look at a very generic set of random matrices, right? So our matrices are U sigma V, where U and V are random rotation matrices, and sigma can be arbitrary. So these are the set of rotationally invariant matrices, if you want. And we have this result that m over d should be larger than 1 plus beta over 2. And we have this relation here, in which indeed what you see, that is just depends on the distribution of eigenvalues that you find. And if all your eigenvalues are 1, you come back to the sensors. If you plug Marchenko pasture, you will come back to this one, and let's generalize the situation.
Florent, okay, this is all noiseless models? There's not
all this is noiseless, yes. Yeah.
Okay.
Now, what about the strong recovery? And here it has to be noiseless if you want to give an answer. And it's actually simpler to state. It's very trivial, actually. What you need if you want to have a vanishing error is m over d larger than beta. So larger than 1 in the real case, larger than 2 in the complex case. And that's interesting because that's exactly what you will guess naively by counting argument. So again, so that was shown for the real case here for Gaussian matrices. In this paper, they show it for unitary matrices, and we actually generalize this to these ensemble. Now, to be a bit more precise, that is our main result in this case, which of course will not discuss the equation, but essentially it's a proof of a replica result. So there is that kind of replica free energy that appears all the time in statistical physics literature. So you have this complex function that you need to extremize. If you manage to extremize it, well, replica theory tell you that the minimal mean square error you should get in this problem is 1 minus qx, when qx is one of the elements you have to extremize over. Actually, you have to take a soup here. So we obtained this result with statistical mechanics method, and then we managed to prove them using interpolation method. And in fact, we tried to prove these results for all matrices that were rotationally invariant, and we could not do this. But we managed to prove it for all matrices of the form WB, where W is Gaussian and B is arbitrary. Okay, so it's still kind of a very large set of matrices, which is larger than just the IID Gaussian that we use, and in particular, it includes all correlated Gaussians. Right? So that means that for all these matrices, we can actually tell what is going on with a complex and real phase retrieval, and also compute the minimal mean square error. So let's forget this ugly formula and look what it actually means. This is what it means. If you increase the number of measurements and you have a Gaussian matrix, this is a complex case, all right? So your error is 1, not better on a random guess, until you meet the weak recovery threshold, which is at n over d is 1. Then it decay. And then exactly at 2, you should expect to jump to 0 error. Okay? For orthogonal matrices, and that was shown by the group of Maleki et al., actually, the weak recovery is equal to the strong recovery, and transition is exactly at 2. Okay, so this is what should happen if you are able to compute the minimal mean square error. But of course, I didn't tell you how to do it. This is a statistical or information theoretic prediction. The question is, what about efficient algorithm in this case? Okay, how would you do it in practice? Now, for those who know me, you will not be surprised, of course. I tried message passing. What else? We have now a very good control about what approximate message passing and BP is doing. In fact, for the kind of problem discussing, we have something called VAMP, which is vector approximate message passing. It can handle all these rotationally invariant matrices, and it has been written for phase retrieval in this work. So we can just use our standard technology, run this algorithm, and see what's going on. And we can analyze its results with the state evolution techniques. Okay? And what do we find? We find what you would expect, I guess. If you run IMP, well, IMP is doing a good job. These are the points. These are the simulations. Except, well, if you zoom close to the information theoretic threshold, you see that it's not exactly what quite we expect. Again, you can compare, with the state evolution techniques. And if you zoom here, well, you see that there is a very small region where you have the information theoretic transition at 2, while algorithmically you find something good at 2.1 or something, and you have the same kind of phenomenon for the orthogonal matrices. Okay, so this is what we expect. We have discussed this thing many times. These are the difference between the easy and hard transition. Yes.
What is the prior here? Like
oh, this is just X on the sphere.
Just and for the simulations, you just use some X random on the sphere.
Yes, but actually it doesn't really matter because being on the sphere is just a constraint on the norm. So as long as you pick a vector which is not correlated with the matrix, it's basically the same all the time.
Thanks. Yeah.
All right. Now, here I have been lying to you because I've told you that the analysis of IMP, you can do it with state evolution. It's not actually quite true in this problem because, well, because there is a symmetry between, +6 and -6. And because of this, when you try to understand rigorously what is going on with IMP, if you run state evolution, you should start exactly at a guess which does not break the symmetry. But if you don't break the symmetry, IMP will stay there. Now, random initialization works in practice. This is how I obtained this plot. But if you just initialize IMP randomly, then your state evolution analysis is not rigorous anymore. So it's a bit annoying that, that this problem is there, and it is there, as far as we know. And one way around it, if you want to study perhaps more rigorously what's going on with weak recovery, is to look to spectral methods. And in fact, that is something that was done 1 or 2 years ago in the series of work, first by Andrea and Marco, and then in a group of you. All right, so when I think about a spectral method for any problem on which I use message passing techniques, I always think about 2 ways to derive them. Okay, one way is essentially the one we used back then with Chris, Joe, and Alan, and Pan, and Lenka, and Elkanan in 2013, when we linearize BP, we just linearize the message passing recursion, and that's what leads to the non-backtracking matrix. Okay, so that's one way. You can do it, you can write it. In fact, you can generate, not only you can do it, but it was done. It was first done, I think, in this paper. And if you do this, you obtain indeed a matrix which is here. It's actually a non-symmetric m times n matrix, so it can blow up if you have many measurements. But it's a well-defined problem, and then you can try to analyze what's going on with random matrix theory too. Now, a different techniques which I like a lot is not to focus on message passing, but to focus on what message passing is solving. And actually, what message passing is doing, BP, what it is doing is to try to evaluate the better free energy. Actually, IMP is trying to solve the tap free energy, if you want. If you are using these matrices, which are not IID Gaussian, there is another term, which is a Plewka free energy. So the Plewka free energy is, there is this thing called the Plewka hierarchy, which is a systematic correction of tap whenever your matrix is not IID Gaussian. Okay, and it's a very nice. There is a deep connection between Plewka and Kikuchi, for those who know, and I'm not fully understanding that. I think there is room for explanation. So instead of trying to linearize the message passing, I can say, well, the message passing is trying to find an extrema of a free energy. So maybe what I should do is to be at the trivial extrema and to look at the Hessian. And the Hessian of the free energy will tell me good direction to go. Okay, and that is something we actually did back then for community detection with Ala Sadeh and Lenka Zdeborova. And interestingly, if you do this, you have a matrix, which you find here, which is, I don't know, much simpler. It's n times n, it's symmetric, and so it looks much nicer. And it has this form. Now, that's interesting because that's exactly the kind of object that was studied in this paper by Andrea and then later by Yulu et al. In fact, what they did was to study a matrix of this form, okay, that were linear combination of the matrix elements with a function tau applied to the measurement y. And what they did in these 2 works, so first Andrea proposed this, and then he found one form of tau that was good enough to find the correct transition. And then in this second work, Yuelu optimized over the whole set of functions and tried to find the best function. And interestingly, if you try to do this, you try to find the best function, what they found, much before us, was exactly what is directly given to you if you just compute the Hessian of the free energy. So I think this is nice. It's probably saying that, yes.
Florent, there is something that I understand in this thing. I mean, in our paper, actually, we do both calculations, and actually we show that they are equivalent. I mean, there is some, I don't
Yes,
more. There is some simple matrix transformation.
Yes, but in your paper, you are looking to a Gaussian.
Yeah, sure. I mean, I'm just saying, you know, the two metrics.
I know. I will come to this, but you are spoiling the next slide.
Okay.
Yes, you're right. Okay, but so if you, yes, okay. So first remark. And remark two, what is interesting here is that if you look at the expression you find here, well, the only place where the spectrum appears is here for these averages. So you actually do not depend on the spectrum in your spectral method. You don't need to know the spectrum. You need to know the matrix, but you know. So that means that this form, which is the one obtained in the second paper when it was really optimized, it suggests that it should be universal, and that actually that's the best function, whatever the spectrum is. And in fact, we are going to see that this is true. And I'm almost going back to Andreas. So, you know, what Andreas said is also true in, you know, beyond Gaussian matrices. So this is what happens for method A. Okay, so it's a non-symmetric matrix. So if you diagonalize it, you have complex eigenvalues, and you have interesting phenomena that at some point you have one eigenvalue that goes out, that is informative. And what is very interesting, that there is a second eigenvalue which is informative, which is here. Okay, these two eigenvalues are informative. Of course, it's harder to obtain this one via iteration. Now, when we do the Plewka, Hessian, or Ueluz method, if you want, you know, it's something very similar. You have at the exact same point, you have one eigenvalue that goes out, and which is informative. Now, what Andrea showed for Gaussian matrices is still true here. And there is an equivalence between the two. And what is interesting is that this guy here doesn't correspond to the guy that goes outside, but to this one. And the same for, you know, this guy corresponds to this guy. So somehow the Plewka is missing the leading eigenvalue here. So this is connected with the fact that, you know, the way you derive it, you're not completely looking at all the negative direction, but that's what we found. Now it looks like maybe this is bad, but interestingly, you will see that this eigenvalue here has a much better overlap with the planted true than this one, which is surprising, but this is true, and I don't have an explanation for this. So there is a connection between the two, and this is, you know, the kind of thing we find. So if you have complex Gaussian matrices and you apply this method, this is a transition. So this is the method of the first method by Andrea, which pick up exactly the right transition. And now, if you use the method of UA, which is the one where you further optimize the function to find the best one, and it also corresponds to the TAP Plewka Hessian, you have this curve, which have a lower error. Interestingly, if you use this method, which I thought would be the best, naively, at least when you linearize TAP, you know, well, it seems that you have something better than random here, but this is just random fluctuation, so it's okay. It's systematically actually worse than the two others. All right, so I still think this is interesting. And of course, then you can generalize this to matrices which are not Gaussian. And the interesting thing is that then, you know, this Hessian matrices don't need to be adapted. You don't need to further optimize. It's always giving you a very good overlap, and that's the correct transition all the time. So I found it nice. Okay, these are other examples for other matrices. So I found it nice that, you know, it's not a new discovery. We knew about this spectral method, but it's kind of nice to see that they do what we expect them to do. You know, if we derive them from first principle of what we believe a good algorithm should be, we find them back. And this is nice. And you can generalize them to other problems such as Poisson noise and so on and so forth. Okay, that's what I wanted to tell you for the first part. I still want to tell you something fun about this problem, which is, okay, and that's connected to some of the questions I had. What happens if we have a better prior for X, okay? So of course, one thing that comes to mind is sparsity. Everyone has been looking to this. In fact, I was looking to exactly this problem a few years ago, and we wrote this paper with Jean Barbier, Nicolas Macré, Léo Miolan, and Lenka when we looked exactly at this. Long story short, that's the kind of phase diagram you have for real phase retrieval. for sparsity. So, you know, your number of measurements with respect to the dimension, which is now P, I'm sorry, should be, you know, the n over P should be larger than rho. So, you know, the number of measurements should be larger than sparsity, otherwise it's impossible. What's interesting, you have a hard phase here, and like I showed this during the bootcamp, and you see that the hard phase stops at 0.5 here. And so this means that it's really impossible to compress something in this case, because you know, you don't have good algorithm that works here. And another phenomenon which is interesting, which I don't think anyone picked up, but I think it's a funny remark, is that what we found is that weak recovery itself is hard. Like here, we don't know of any algorithm, if you know, if n over p is smaller than 0.5. I mean, actually, what I can say is IMP doesn't work, doesn't beat a random guess. And so I strongly suspect that, you know, any SDP relaxation or problem like this will have the same problem, but I've never seen anyone looking at this. I think it's an interesting thing. But okay, so this is for sparsity, okay? But this is so 2015, right? Now we're in 2020, and it's all about deep learning. So what happens if you use more complex prior? And of course, this day you can do a very interesting prior, say that, you know, X is an image. You will say, fine, I will train a set of neural network on the set of all faces, and then I will have a GAN or normalizing flow or whatever you want, and you could generate a very good prior. So you say, you know, X has been generated starting from random vector Z, and then it went through a neural network, and it was like this. Now, if X is generated by that West network, and I do something like phase retrieval, how hard is it? All right, I have no clue. Okay, it's really hard to analyze this thing because, of course, if you learn these W's, I don't know to analyze this. One thing we can do, of course, is to say, well, you know, life's too short. Let's assume that all the W's are random. Now, then we can analyze everything. Okay, then it comes back to things that we can analyze, and it generalizes very well some of the things we can do. I will go. You know, I just want to show you, for instance, how you can compute mutual information for such a problem. So again, for the sample problem, we knew how to do it. So if you have X, you get Y. That's actually what we got for the mutual information. Actually, this is the entropy of Y. Okay, it's an extremization of a function. Okay, and with a bit of rewriting, you can show that this is the extremization of the entropy of X plus some noise plus some function, which has not a nice face. Okay, so but the trick is the following. If you have a two-layer problem, so X now has been generated by one-layer neural network with a random matrix, you can heuristically derive the solution like this. Okay, so Z is generated X, and then from X you get Y by this phase retrieval. Okay, forget about Z. Let's assume that the formula we had before is still valid, even though X is not IID now, it's a complicated problem. Okay, so then that's the solution, except now we need to evaluate the entropy of X. But since X is not IID, this is not entirely trivial to do. Fair enough, but if you look at this, and you remember what X is, well, this is the entropy of a variable, which is square root of m phi of WZ, but this in itself is a generalized linear model. It is the kind of exactly the problem we solve here. So you can take this formula and plug it there, and putting everything together, you have now a formula in which you have to optimize over, well, twice as many of variable. Okay, and you can repeat this, that's kind of Lego principle ad infinitum. And we actually prove rigorously that this is true at least for 3 layers. And it's probably true for more layers, but then it's a bit harder. The trouble is to prove the existence of the free energy, but you know, except for this, the proof goes through. And you know, this heuristic derivation is telling you how this thing goes together. All right, and of course you can do the same kind of thing with IMP. Won't go into the detail. I just want to advertise distribution that we put on GitHub that can do all this problem, and it's very versatile. Now, what is going on then? So it's very interesting. Once you put structure in your prior, it changes everything. Now, that's, for instance, what happened if X is not IID with sparsity, but ReLU of a matrix W times Z, and Z is Gaussian. Okay. Now, if you look at the number of freedom, it's not anymore given by sparsity, but probably by the size of Z. So that's the number of latent variable, if you will. And now this is your new phase diagram. And this is to be compared with the one you had when your only information was sparsity. And you see that it changed quite a lot, with, from here to here, you have changed things. First of all, your hard phase is much smaller. Suddenly you can do compressed sensing. And it's perhaps not surprising, but the effect is striking. Generative models are really, really, really helpful here, not only in terms of statistic information, but also algorithmically. And another interesting point is the following one. What happens if you are using a deeper neural network, still random? Well, you see that you start to converge. You basically kill here the hard phase with depth, and here, it also goes to zero. It seems to go to zero, but much more slowly. Not clear, actually. I think there is still a gap. And in this paper, Paul Hand and Tal actually designed one special scaling in which they could completely destroy the hard phase. It was, of course, a bit made up, but it was very interesting that you could do it in principle for such problem. Okay, and I think this is interesting, and it shows that we can start to analyze correlated data, and that good priors, can reduce drastically statistical to computational gaps. All right, almost my last slide. There are many more generalizations to what I have presented, even in the second part. Again, I discussed phase retrieval. The theory is not limited to phase retrieval. Any generalized model will do. We did it also for matrix and tensor factorization. You can also adapt spectral method to use deep priors that give you a clever spectral method that perform better than simple ones. Okay, I'm really done, and I want to thank my collaborator and students and postdocs on this project. And as Dimitri said, we are looking for talented postdoc and student. If you like the view, and if you want to go in EPFL, write me a mail.
Okay, thanks very much, Florent. Let's thank. Let's open for questions. If you have questions, feel free to post it on the Q&A or just go live.
I made a mistake. I lost your face. I don't know what I did exactly. I lost the screen.
We can see you.
Yeah, I can see you, but I'm at disadvantage, but that's fine.
I don't know if nobody has. I have a small question. So
yes.
There is so you have results for these orthogonal ensembles, and then do you know? I didn't follow this. Is there any progress being made about coded diffraction patterns? That is, basically partial Fourier transform, because that is a more realistic model than.
Yes, very good. So I think that there is a student of Ariane who might be listening right now. I don't remember the name. Maybe a student of Ariane Maleki who actually proved a result for random subsampled Fourier. Okay. So in the case of X being Gaussian, okay. I think so, yes. So that is nice, right? It's actually the only result I know for fully deterministic matrices. And so this is nice. It's restricted to X taken on the sphere, but that's still remarkable. And it's the only one I know that goes beyond just random matrice like the rotation, your rotation invariant and Gaussian.
There's a question from Prasad. Prasad, if you want to go live and ask your question, please go ahead. If not, I will.
I found a way to find you back. It's good.
Okay, Prasad, you. Okay, I'll read his question. What is the easiest prior, i.e., are there natural priors under which the phase retrieval has no hard phase?
Like natural ones. I don't think so, but there is a matrix for which it has no hard phase. Now, there is a way to design, so if you take product of a matrix, which is a product of two Gaussians, and you select the aspect ratio to, I think it was 1, I'm not so sure, but we write it in the paper. So there is one aspect ratio in which when your measurement matrix is a product of two Gaussians, that entirely kills the hard phase. And that was surprising to us. That was, you know, otherwise, no, I don't think I have seen, you know, natural sample priors for which there was no hard phase at all.
If you make all the entries of the prior integer valid and make it noiseless, then there is a sample size of 1 that is needed, and it's always in the easy phase.
Okay, yeah, fair enough.
I'm not sure it's natural, but maybe that's an example. Sidhan, go ahead, Florent. You were saying something.
No. I'm listening.
Sidhan, I know you can go live. You want to ask a question?
Sure. Yeah. So actually, I was curious about the two ways of getting spectral methods that you mentioned. One was linearized AMP, the other was the Hessian. So I guess in particular, the question I was wondering about is whether there's some kind of like determinantal identity relating the two, just because at least for the analog of beta free energy, there's like this Ihara-Bass formula.
Yes. No, they should be connected, of course. You know, but for instance, for community detection, they are connected through Ihara-Bass formula. In the work of Andrea and Marco, actually, you know, they showed some connection. Now, I'm not fully understanding exactly everything now because, you know, this is slightly more involved because now it's less VAMP and I don't, you know, it is slightly, you know. And also, there are many ways to do the linearization. So I think there should be a one-to-one correspondence. That must be true. Now, when you do, you know, the linearization, there are many ways to linearize. You know, you say, okay, now I take fixed point of everything, I perturb here, and maybe I will assume those guys will not change. And so some, you know, for instance, AMP or VAMP actually do not have n degree of freedom. It has 2n plus 2n degree of freedom. So if you really compute the full perturbation matrix, it's really complicated. So you say, okay, fine, I will look to this subset. And this is what I have done in both cases. Okay, it's not the true Hessian, it's not the true perturbation matrices. So it's, you know, and then you have this complicated object and you say, okay, let's try to prove that this thing has the same eigenvalues and to try to get a Ihara-Bass formula. So I don't know yet how to do this totally, you know, in a systematic way for this in this problem. But at least I know that if you do it that way, the second, you know, the eigenvalues inside the bulk for method 1 correspond to the eigenvalue outside the bulk for method 2. But it's probably not the only way to do it, and there is probably you know, more way to think about it.
Okay, yeah, that's reasonable.
Yes, sorry.
Yeah, I mean, perhaps if I can add a comment. Yeah, there is, if you look at you know, our paper, there is a relation via determinantal, you know, connection.
Oh, cool.
I mean,
okay.
it's something I don't remember exactly, but it's something relatively simple.
Thank you.
There's a question by Yuhong Wu. Is there a version of the replica symmetric formula for the Bayes risk you showed for IID matrix X for rotational invariant X?
For the Bayes risk of which variable?
For the when X is rotational invariant. Okay.
Sorry, but X is the vector, not the matrix. I'm a bit confused.
Oh, right, should be for the matrix. Yeah, I'm trying to interpret the question myself.
Yes, in fact, I think this is essentially the one I gave. here, well, oh, yes. So the answer is yes. There is one. It's in our paper. Now, the question is it a replica formula or is it can we prove it? So we know to compute the base risk, I think, if X is spherical for almost all rotationally invariant matrices. If X is not spherical, okay, so let's say that your vector is Gauss-Bernoulli or something, the proof only works for Gaussian matrices. I'm pretty sure the formula is correct for rotationally invariant, but I don't know to do it in this case. I don't know to prove it.
Could I ask a question?
Yeah, go ahead.
So when I first heard about this problem from Veit Elser, who has these alternating projection methods and, you know, divide and concur and ADMM and that whole business, do we know anything about the performance of those algorithms on these random problems? Is there any hope of analyzing them and comparing them with these methods? Does it make sense to linearize them, et cetera, et cetera?
You really like this algorithm, right? You keep asking this question.
I always, it's a crazy kooky algorithm.
Yeah,
of course I like it. Yeah.
And it works well. So, okay, two answers. First one, I have no idea about divide and conquer. Second question, actually, when you run VAMP, you know, this vector approximate message passing, which is the same as something, you know, it's the same as something called expectation maximization, and in turn, it's the same as what physicists call plevka, and it's again the same as what Kabashima called ADATAP. And this algorithm is extremely similar to ADMM. And indeed, the way it works is by solving, you know, things on one side and then trying to solve on the other side and blah, 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 until you converge. And when I'm saying it's very similar, it's more than very similar. If you do the map version of the algorithm, you know, to minimize the cost function, you can show that they are exactly the same. There is a one-to-one correspondence.
But don't those algorithms also have this weird over damping that, you know, you will cause the algorithm to fly away from local minima and so on?
Well, you know, at least VAMP works. But you know, the thing which is interesting between the difference between VAMP and ADMM and everything is that in, you know, this vector message passing, at each steps, you are kind of changing the constant of your ADMM in a way that will help you converge. And you know, that kind of help, that kind of thing. I mean, I find it's nice that we start to make connection with optimization algorithm. In fact, we used this for studying other problems, but yeah, it's not the place to discuss. But at least there is a connection here, and so that's interesting.
Any further questions? As we are slowly moving to the canceled open problem sessions. So if no further questions, let me suggest that we thank all three speakers of this morning, and we will resume tomorrow. Thank you all, and see you tomorrow.